Okay, great. Welcome everyone to our session titled A New Activity Mart for Increasing Student Success. My name is Kyle Unruh. I'm the Interim Director of Data Services and Solutions at Unizin. It's a mouthful of a title, but I try to get through it each time. I'm joined by my colleagues from the University of Florida, Jose Silva Lugo, who is a data scientist, and Min Pham, who is the Learning Science and Analytics Specialist at University of Florida. Also, a shout out to Heather Manus from Florida and Sarah Bull from Unizin. They also were big contributors to this project. They're not presenting with us today, but they definitely had a presence in the work that we're presenting. They're really excited to be here today. I will also be monitoring and moderating the session. So while Jose and Min are presenting, if you have any technical questions, or if you have trouble hearing anything or seeing anything, just let me know, and I'll work with our Kaltura friends behind the scenes to help get anything sorted. So yeah, just ask any questions in chat, and we'll try to get that solved for you. At this time, I'm going to hand it over to my colleague Jose to get us going.
We started our project by building predictive models to make prediction of students at risk, and we found that Canvas performance variables were not good predictor variables. So we searched in the literature for activity variable because we found a strong correlation between these variables and student success. Most of these studies basically work with individual activity variables. So we decided to develop a participation index by aggregating the activity variable and establishing the relationship with the student letter grade. The variables of interest were chosen based on the availability in Canvas, and each variable was extracted from the Oracle database by using SQL procedures in SAS. A total of 67 courses belonging to 11 colleges and 28 departments were chosen based on the following criteria. A course-based department represented a 1,000, 2,000, or 3,000 course level and with large enrollment. These were the variables of interest that we chose. Per week, the number of logins in the course, time spent in hours, number of pages viewed, number of submissions, time spent in minutes, number of files viewed, number of conversations. And the participation index was calculated as the normalized weighted average of the student activity variables. In this slide, excuse me, we describe what we present 4 charts. In each chart, we have the participation index in the y-axis and week number in the x-axis. The brown reddish line is the mean participation score for A, B, C, and D students. And the green line is the mean participation score for all the students. And the number that you see at the top right corner of each chart is the number of courses in which we found this pattern out of the 67 courses. As you can see, the mean participation score for A and B students were above the mean participation score for all the students. And the mean participation score for C and D students were below the mean participation score for all the students. Out of the 67 courses, we found low percentage though. And these results were not good for predictive analytics, so we decided to request Unizin to derive the activity variable for us following the data models of Unizin data platform. And these were the variables that we requested Unizin to create for us in the new Mart Taskforce UFIT folders. The number of sessions 30 minutes, total action 30 minutes, total time second 30 minutes, number of file view, number of submission, number of conversation, number of tool launch, and the weekly page view.
All right, thank you, Jose. So as Jose mentioned, some of these data fields came from tables called task forces. So in a lot of the exploratory analysis that Jose was mentioning, in parallel, Unizin was embarking on 3 sort of parallel task force initiatives. The time frame for this was between 2021 and 2022, and there were 3 different focus groups for these task forces. One was on a new Unizin e-reader, which is not in scope today, but was one of the task forces. The other 2 does have overlap with the exploratory work that Jose was mentioning. One is advising in student success, and one was on faculty and student success. And the goal for these last 2 task forces that I just mentioned were to build data assets on top of the Unizin data platform specifically for these audiences. And the output of these are the Taskforce Marts. So on that slide, that 2 slides ago, on the left-hand side, some of those task force sort of fields, that's where these come from. So going into a little bit more detail, these Taskforce Marts were sort of developed with looking at use cases and sort of priorities for both faculty and advisors regarding student success. And one of the common themes we came across was a need for a weekly record of student activity and interaction with course assets. So we're considering things like discussion posts, files, assignment submissions, tools launched per student, per course, and also per week. So we can sort of look at this as a timeline from the beginning of the semester to the end of the semester. It was also important for us and for this audience to consider what we call different levels of inquiry. So this is sort of different ways to aggregate and do calculations. So the level 1 Mart, so the entry point to these Marts, is the per student, per course, per week numbers. So these are the raw numbers of submissions, raw numbers of discussion posts, the number of files accessed, that sort of stuff, per person, per course, per week. And the level 2, so builds on top of level 1, looks at the averages of these and sort of the aggregate numbers. So we can do things like, for a course, what's the average student doing? So we look at all the different file clicks and what is an average of all of that to look at what sort of the mean or the average student behavior is for that course. When we distribute these slides, you'll be able to use sort of these bulleted links on the right to click directly into the data mart documentation so you can see all the schema and fields if that sort of technical level of detail is of interest to you. Specifically for the work that Min and Jose are doing, there were 2 key Mart features based off of how we have this weekly timeline per person, per course, per week with the levels of inquiry. And the 2 key Mart features, what we call interaction sessions and then normalization. So the interaction sessions are a way that we do a calculation for how much time a student spends in a course in Canvas. We do this by looking at an ordered sequence of clicks that we can see attributed to the students. And this is in the UDP event data, which is adhering to the caliper standard. So we can look at the time deltas between clicks. So if there's an event by a student at, say, 6 p.m. and the next click is at 6:05 p.m., we can calculate a 5-minute delta, which attributes 5 minutes of time spent in the course. We don't want to just take every single time delta, though, because a student might have a click in the evening, go to sleep, and then wake up in the morning and start interacting with their course again. And we don't want to count the 8 hours that they were sleeping as time interacting with the course. So we have what's called a 30-minute functional cutoff. And so later when you see sort of the fields again that we use, some of the fields are suffixed with _30 minutes, and that's the cutoff that we're using. So the time delta, in order for the time to be counted towards interactions, needs to be less than or equal to 30 minutes, or else we assume that the amount of time does not count towards interacting in the course. And then in order to find the total time a student spends in a course, we add up the total time deltas that we see for those ordered grouped events. And that was a really key interaction session. Interaction sessions were a really key metric for a lot of the work that Min and Jose were doing. The second key feature was normalization, and this came in that's level 2, level of inquiry, Mart, that I mentioned before. So the important part for this is we're able to look at an average course peer. So in the level 1 table, we can have totaled activity numbers. So we know the total number of assignment submissions per student per week. So 5 assignment submissions for a student might be what we see in the data. But how do we know if those 5 assignment submissions are high or low for that student for that week? We need some sort of baseline to compare against, and that's how normalization comes into play for this work. So we use min-max normalization against average course peer, against the average course peer to yield context for all the submission behaviors. And the distance from the average behavior is really what of great interest for this project. If a student is kind of adhering to the average behavior, that's perhaps to be expected. It's sort of the extremes that are perhaps of greater interest. So a little bit behind the scenes, we have these different levels of inquiry and these calculations and these Mart features. To work with Jose and Min, we created what's called the UFIT data set in BigQuery, which lives alongside their UDP data. And this presented a safe workspace for all of our analysis. We copied over the Taskforce Marts and any helper data into that data set. And then we initiated scheduled queries so that every day when new data, new learning data and behavior data came in, we would append those results to the existing data that we copied over so that we always had a fresh, cost-effective snapshot of what was happening for this analysis. And we'll get more into depth with that with Min a little bit later in this presentation. For now, I'm going to hand it back to Jose to do more on the exploratory data analysis.
The exploratory data analysis was carried out for spring 2021 and 22 because these were the 2 semesters in which the predictive analytics was implemented. So I'm going to describe how we handle the missing values and outliers, the graphical depth of normality, principal component analysis, and cluster analysis for the activity variable that we just mentioned and 3 performance variables. This table presents the percentage of missing values per week in spring 2021. The performance variables were the target variable, grade points per credit, and 2 predictor variables, cumulative GPA at the start of the term, and the normalized current score per week. The rest are the activity variables that we just mentioned. This rectangular highlights the normalized submissions, conversations, a total, and 2 launch. They have percentage equal or greater than 40% of missing values. The numbers in both phases are the minimum and the maximum. We found exactly the same result in spring 2021 and 22. And for that reason, we decided to temporarily remove this variable from the predictive modeling analysis. However, they were included in the dashboard visualization. From now on, I'm going to describe the result of the exploratory data analysis for the merged dataset spring 2021-22 week 2 only, because week 2 is the week with the highest activity, and because the results of the exploratory data analysis between week 2 and week 8 were very similar. The graphical depth of normality is presented with a histogram and the box plot. As you can see, grade points per credit and cumulative GPA at the start of the term, they are skewed to the left because they have outliers, and the normalized learning environment, current score at week, is by more. Now, normalized section, actions, and time, they are skewed to the right and with mild outliers, and they have very similar shape in the distribution. These are mild outliers. In the raw data set, there were mild and string outliers. However, after normalization, the string outliers became mild outliers. We extracted, analyzed these mild outliers. They belong to the distribution of the data, therefore we didn't remove them. Normalized pages and normalized files, they were skewed to the right without outliers. Now, we have to take in consideration there is a high variance in the distribution of this variable. In addition to that, the shape of the distribution is going to have a very strong influence in the result of principal component analysis and cluster analysis, as we're going to see next. Principal component analysis have been mainly designed to reduce the number of variables. However, for the predictive modeling purpose, we have very few number of predictor variables, and we were mainly interested in the amount of variance the principal component were explaining for the linear combination between the target variable, grade points per credit, and the predictor variables. So we first calculated the component metrics without rotation, then we rotated the principal component with very much rotation, and these are the results. We have three variables in principal component 1, normalized session actions and times, and in principal component 2, the cumulative GPA grade points per credit with high loadings, and normalized pages and normalized files in principal component 1 with medium loadings or moderate loadings. At this point, we needed to decide which component we're going to retain. So we use the script plot and parallel analysis, and both methods actually advise us to remove the third component. So this is the result after removing the third component, and you can see that the variable with high loadings and medium loading, the loading don't change that much. It's just because the third component only displayed 12% of the variance and it didn't have any influence in the loadings of the variable with high and medium loading. Therefore, it makes sense to remove the third component. Also, you can see that only one variable, normalized current score a week, had low loadings in the first and second principal component. Notice that variable with the same distribution has similar loading as well. These two principal components explain 52% of the total variance, 69% of the variance of the cumulative GPA, 68% of the variance in grade points per credit, and between 64 and 77% of the variance of normalized session actions and time. This result allows us to state that we choose good predictors and good target variable just because principal component explain a high percent of the variation of the linear combination between the grade points per credit and the predictor variables. Cluster analysis was implemented by using two distance matrices, cosine angle and Euclidean distance, with 9 agglomeration method. When we did the cosine angle and Euclidean distance with average linkage, single linkage, complete linkage, one minimum variant linkage, and the variant linkage with heat map, we find a total of 9 clusters, but very similar clusters with 3 cluster solutions. And I'm going to represent all of them with only one cluster, which is the cluster and the dendrogram of the one linkage and Euclidean distance. We can clearly see 3 cluster solutions here. Cluster 1 with the standardized action times and session, cluster 2 with standardized pages and files, and cluster 3 with standardized grade points per credit, the cumulative GPA, and the standardized learning environment current score per week. As you can see, these are exactly the same group of variables that have high loadings in the principal component, medium loadings in the first principal component, and high loadings in the second principal component. Again, the shape of the distribution influence in what exactly the cluster solution is going to be. In this slide, we present the result of the hierarchical cluster analysis and heat map. In the y-axis, we have the dendrogram. In the x-axis, we have the predictor variables. And this is the heat map. This is the coherent pattern of color between red and blue. Red means highest score Euclidean distance. Blue means lowest score Euclidean distance. And we can see similar pattern here in the cluster 1 for the standardized sessions, times, and action. Similar patterns again for standardized pages and file, and another 3 similar patterns for the standardized learning environment current score per week, the grade points per credit, and the cumulative GPA. As you can see, they are exactly the same cluster solution that we found in the previous, that I presented in the previous slide, and this is the same group of variables that we found with low and medium loadings in the first and principal component during the principal component analysis. Therefore, we use the result of the principal component analysis and cluster analysis to help us out to design the layout of the dashboard. We can ask questions such as which variable should be next to each other, or which variable we should be prioritized. Predictive modeling must start by indicating that the University of Florida has unbalanced data in all semesters, not only in spring 2021 and 22. In spring 2021 and 22, we had 6 and 7% of failing students. And for that reason, the University of Florida has unbalanced data. Now, if you look at spring at the merged data set, spring 2021 and 22, the percentage of missing value vary between 5 and 7%. This is critical for predictive modeling. Why? Because the models are going to learn the internal structure of patterns in the data set, and they are going to predict more passing and failing students. Therefore, we needed to use several techniques and methods in order to improve model performance. And this is the summary of all of them. We try response variable versus normalized response variable, manually adjusting the optimal cutoff, boosting the true negative, 30% oversampling, and for resampling techniques. We remove significant predictive variables. Also, we remove the student with low engagement and passing the courses, and adjusted the parameters in the model by using the CARE package. The best results were found by the combination of normalizing the predictive variable, boosting the training set, and also optimizing the cutoff by using manual processing. These are the 6 models that we use, and the best model was the random forest that made prediction between 85% and 89% between A2 and week 8 of the semester. Now, in the literature of early prediction, you're going to find percentage of sensitivity and specificity between 70 and 80%. If we take into consideration this standard, we're going to need to intervene more than 10,000 students per semester, because the population to the University of Florida is at least 35,000 students per semester. We needed to increase that standard to at least 85% per week sensitivity and specificity in order to intervene approximately 6,000 students. However, this project has not finished yet. We are still working, trying to improve sensitivity and specificity for the University of Florida. Now I'm going to hand it to my co-worker, Minfa.
Thank you, Jose. So, Jose, what has laid the groundwork for our dashboarding, and during the process to retrieve the data from our dashboarding, then we encounter challenges regarding writing costly queries. Writing costly query, and to encounter this challenge, then we have been working with the Unizin team to figure out the strategies we can optimize the queries. And we have been receiving tremendous help from Unizin team, especially Sarah. I can never thank you enough for all the help you have provided for us for this project and many more projects we have been doing now and in the future. And when working with writing queries to pull the data, then I realized that the queries that are very costly are queries that pull the data from the event tables. For example, in this query, then we aim to pull the data to visualize student course activity, hourly activity per day. And we limit our data to only pull the data for the current semester with a fixed time date in the, as you can see in the event time limiter. And even though we limit our data to only navigation event for in this query and pull only the data for the current semester, this query still costs hundreds of gigabytes to run on a daily basis. And Unizin recommended no more than 100 gigabyte max per query. And this query requires constant intervention to update the date of each semester so that we can pull the data for only the current semester. So it is not efficient for maintain this query as well as scale this query on a semester basis. So we reached out to the Unizin team to see what we can do to improve our work process and reduce the cost to run this query. So Kai, can you talk about the optimization we can do with this query?
Yes, for sure. It was great working with Min. And again, another shout out to Sarah. She did a lot of really great work on optimizing these queries. The query window that Min was showing was our BigQuery interface, and all of the UDP is built on top of Google Cloud. And so we have to have optimization in mind when we write queries on BigQuery. It's really great at large data sets, which is what the UDP event store is. The cost model, though, is charged based off of the number of gigabytes or terabytes that are scanned per query. So that's why we needed to have an optimization approach for this, where if we ran the 200 gigabyte query that Min showed multiple times, it could become very costly. But one thing that's interesting about the way we were writing those queries is, the way that we were scanning was, hundreds of gigabytes of historic data, but we weren't really storing hundreds of gigabytes of historic data. There were a lot of filters in the where clauses, like we were only looking for navigation events, we were only looking for canvas events, and we had some other filters that I don't recall, but we essentially didn't need every row that we were scanning, even though Google BigQuery was charging us for every row that we were scanning. So the optimization techniques that we employed were to run one large query. So we couldn't get away from that. We still needed the historical data, but we only needed it once. So we kind of ate the cost of one really large historic query, large query to get all the historic data, and we stored that into a table. And what we did is, on top of that, we wrote a series of other queries that Min is going to show that are scheduled queries. They run once per day, but they only scan 1 day worth of data. So much less than all the historic data that was needed to scan before the optimizations. With the 1 day of data that we have scanned every day, it's much smaller, and we have pinned those filtered results to the end of that large query output. So what we have is sort of a helper table that's not the source data set, but it's the rows that we care about, and it updates every day, and it narrows the scope for the exact work that Min and Jose needed to do.
Thank you, Kai. So here is what we have implemented. So as Kai mentioned, that first of all, we need to write the query to create the table that pull on the historic data that we are interested in. And another step we did with this table is we create a variable that will dynamically determine the start date of the semester. And with that variable that can dynamically determine the date, the start date of each semester, and we implement it in our query, then the cost for that original table now it reduced from hundreds of gigabytes to only 440 bytes to run. And and then the next step we did is we create a schedule query, and that query only the latest data, the latest 1 day worth of data, and append that data to the existing historic data table. And with that, then the schedule query, it is run on a daily basis, but the cost is very minimal in comparison with my original query that will require hundreds of gigabytes to run on a daily basis. And besides the tips that Kai has mentioned, then during the process to work with writing queries, then I find that it is writing query, it is not a once and done process. It is an iterative process, and when I work with large and complicated queries, and I have concern about cost, I find that reaching out to Unizin team for code consultations are extremely helpful to identify the bottlenecks and help with improvement for the query time-wise and cost-wise. And another tip I think very important is before, when I first started this project, then I have to without my personal workspace in UDP. Then when I work with event table, I might need to create multiple table common expressions in one query. And imagine running multiple common table expressions, pulling the event data in one query on a daily basis. Then that query might pull most of the institution data usage quota for the day. And that's why when I made the mistake writing too costly query, that the Unizin team caught the issue on the end, and they have one of the steps they have is providing me with a personal workspace so that I can test the query and create the tables. For example, yes, appending the data to existing table, create table and appending the data to that existing table and pull the data from the table I have created to query the data. That might be helpful for our visualization. Then I find having a personal workspace very useful. And the next thing we did is to validate our query results and see how the results work with our visualization. Then we find very helpful to work with the data for only one course. It helps to reduce the time and the cost to run the data. And for our dashboarding, then as Jose mentioned, that our dashboard, then it focuses on 3 components of student learning. And as you can see in the mockup here developed by our boss, Dr. Heather Maynis, then our dashboard focusing on 3 components. The first component provides faculty insight into student access to learning materials, including syllabi and assignments. And the second component provides insights into student learning activity. For example, when students were last seen in a course and how long students spend each time they log in. And the last component provides the summary of student learning and create an alert system for faculty members. And for our mockup and dashboarding, we have made use of a lot of prior works by the Unizin community. For example, as you can see here, we made use of the work by Nebraska University and Indiana University. And the next following slides, then I will show some screenshot examples of our dashboard, which is still work in progress and need a lot of improvement. The first visualization, it provides the faculty with insights about student grade in relation to student activities based on different activity metrics, like Jose mentioned earlier, like 5 view and the time they spend per session. And the visualization to the left, it provides the overall trend for the whole class. And the visualization to the right, it provides the trend broken down by student learning categories like thriving, not thriving, and at risk. At this stage, then we assign A student belong to thriving group, B and C student belong to non-thriving group, and the rest belong to at-risk group. For the next visualization, then we provide insight into student last activity. So faculty member, when they log in, they can see how, for this visualization, then faculty member can see how the last days a student of interest, the last day a student interest was last seen in comparison with the average days the whole class was last seen, and the average day each group of students were lessons. And if they have an over student name, then they can see what percentile this particular student belong to. The next visualization, it provides insight into the time lapse between student first view in relation to the due date and submission date. The eyeball represent for the first view event, and the square represent for the submission date, and the cross represent for the due date. So faculty can see the submission patterns of students. So as you can see, that students tend to submit student right on the due date. And they can also see they can have some information regarding why some students lag behind the class. Maybe they belong to a risk group because of their time management skill, or maybe because they are struggling academically. The next visualization provides student hourly activity per day. So this visualization might be helpful for faculty to time when to send out important notifications for students. The next one provides insight into student use of tools available in the course across groups. And with that, some of the key takeaways we have from this project include the student activity learning data regarding learning performance and student learning behaviors. They are like most of real-world data. They are not normally distributed and contain a lot of now data, which provide good challenges for data scientists like Jose to deal with. And our principal component analysis indicates that we chose good target and predictor variables. And our cluster analysis confirmed the results of principal component analysis and recommended 3 cluster solutions for our dashboard layout. And the predictive modeling Jose did showed that our unbalanced data continues to bring challenges for us, but it is expected that we work with unbalanced data when it comes to student learning behavior and student learning outcome, because we all hope that most of our students pass the courses. So it is common to have unbalanced data. And with unbalanced data, then we have to use multiple approaches to see what machine learning techniques can provide the best model performance. And we see that random forests work most effective with our data. Regarding query optimization, then we see that when working with event data, then it is recommended to use data appendage. And writing query, it is not a one-time task, or we ask for help if we need. And with dashboarding, we find that having a mockup help with the dashboard requirements, components, and provide the reference point for us to provide feedback. And we also find that we don't need to reinvent the wheel when it comes to building our mockup and building our dashboard at all. We can collaborate, make use of the good works that the Unizin team, the Unizin community have been developing. So that's the end of our presentation. And if you have any questions, we are here to answer.
Thanks, Min. There is one question that came in from Bob Spoonmore. Can we clarify again the definitions of thriving, non-thriving, and at risk?
So currently from our proof of concepts, then our team assigns a student belong to the thriving group. Student with B and C belong to the non-thriving group. And yes, the rest belong to the at-risk group. But for the next version of our dashboard, then ideally we want to provide the faculty member with the autonomy to choose what, to identify the cutoff value which they think that students should belong to each group. but we haven't managed to do it with the current version of our dashboard.
We have about 4 or 5 minutes left. So any other questions you can put in the chat. I had one question that came to mind for Min and Jose. So with the random forest predictive modeling and these sort of dashboard mockups that you mentioned, have you started getting feedback from end users? What's sort of the reception? Is that one of the next steps for some of this work? Just kind of curious on like what you guys see as sort of the next steps with this.
Yeah. Let me provide you some advanced information about that. Just recently, Min found that not all the courses have 15 weeks or 16 weeks of the semester. Some courses have 8, 9, 10 weeks of the semester. That implies missing values in the other weeks. So that is affecting the final prediction of the models, in addition to the fact that we have more than 40 grading schemes in all these courses. So in only 67 courses that we review during the preliminary exploratory data analysis that we did, we found 43 grading schemes. So different grading scheme and the fact that not all the courses are actually working during the entire semester is affecting the result for all the courses that we are analyzing right now. So the next step that we are doing right now is to separate the courses that actually are developed during at least 15 weeks of the semester, and we are going to do the data analytics with them.
Thank you, Jose. And I also want to add some more. So, of course, then after we have the first version of our dashboard, then we would like to reach out to the end user, instruction designer, and faculty members to evaluate the usability of our dashboard and to identify if they would like to have more features and more components added to our dashboard. So currently, as you can see in the mockup, then we focus on 3 components: learning material access, student learning performance with the variables identified in the work by Jose, and student summary, performance summary. But there might be other components that faculty member would like to have in the dashboard so that they can provide better feedback and intervention to improve student learning. So yes, we would like to conduct usability testing and interviews with the end users here for the next step.
Great. I think Chris Leyland from Wisconsin had a question, but I think it might have been answered. Chris, let me know. She was just interested in just loving to hear report on what faculty do with this data and what bits they find most useful or helpful. Min, I think if I heard your answer correctly, that's one of the next steps is getting that.
Yes.
Faculty. Yeah. I see one more. Oh, just from Ryan Yang, further clarifying some things. Thank you, Ryan. Yeah, contact information in case anyone wants to reach out for more information.
Yeah, if you want to reach out for any information and code, queries, stuff like that, then feel free to reach out to us.
Great. Thank you. Thanks, everyone. Enjoy the rest of the summit. And thank you, Min. Thank you, Jose, for sharing your deep knowledge with us. Have a good afternoon, everyone. Bye.
Thank you, everyone.
Bye to everyone.